video, I would like to talk about the acidity of carboxylic acids and their derivatives. So let's get back down to the basics. What is an acid? An acid donates a proton. So what things makes it easier for an acid to donate protons? Well, the following are rules for acidity. So the first thing you really want to take note of is resonance, because when you move around electrons, that allows the hydrogen to leave. The next thing you want to look at is atoms. The larger the atom is, the better it is for acids. So we know that goes oxygen, nitrogen, and carbon. And then the next thing you want to look at is polarity. Why is polarity important for carboxylic acid derivatives? Well, because carboxylic acid derivatives are extremely polar molecules. So that is due to this carbonyl bond right here, because the electrons are getting pulled toward that oxygen. So that makes this a very polar molecule, because this is partial negative and that's partial positive. So when you decrease the polarity of a carbonyl, you're going to decrease the acidity. And then the reverse is also true. If you increase the polarity of a carboxylic acid derivative, that's going to increase the acidity. So let's go into our examples. The first thing we want to do is create our conjugate bases. So let's get rid of our hydrogens. We're removing this one. In the amide, removing one of these. In the aldehyde, please keep in mind that we're removing one of the protons here, not this one. And then in the ketone, again, removing a proton from either one of these sides. And then on the ester, please keep in mind that we remove the proton on this side, not this side, because here is where the acidic proton is. So now what do we look at? We've removed our protons, we've formed our conjugate base, we want to look at our resonance structures. For carboxylic acid, the resonance structure looks like this, because we move the electron here and the double bond breaks. So you form a structure like this. And we know that both of these are the same structures, right? They're resonance structures, however, they look alike. So both of these are major contributors. So I'm going to go ahead and write that down. Both are major contributors. The resonance structures for the next four, however, do not produce two major contributors. Let me show you an example with the amide. Because when you move these electrons down here and you move the double bond up, you form a structure like this. Both of these are not major contributors. This is the major contributor for this resonance structure. And the same goes for ketones, aldehydes, and esters. You're going to form a resonance structure like this. I'm sorry, that lone pair is not here. And we know that this is going to be the major contributor, not this. So you don't have equivalent resonance structures here. So that is one of the main reasons why this is the best acid, because it forms a really solid resonance structures where both are major contributors. You can also look at the size of the atom, because we know that over here, for the carboxylic acid, the atom is oxygen. Over here, it's nitrogen. And for the rest of these, it's carbon. And we know that oxygen is a bigger molecule than nitrogen and carbon, so that makes that the best acid. The next best acid would be amide, because you can look at the size of the atom, and we know that nitrogen is bigger than carbon, so that makes that the next best acid. When you come down to esters, ketones, and aldehydes, you can no longer rely on resonance and atoms, because we're looking at carbons, and you can't say that this carbon is bigger or smaller than the rest of these carbons. And you also know that all of these form resonance structures that form major and minor products. So you can no longer use resonance here. That leaves you with polarity. Let's go back to this rule that I was talking about. The less polarity, when your polarity decreases, when you have less polarity, that is going to decrease your acidity. So essentially, that's what we're going to do with what we have left. We want to see which one of these decreases our polarity the most. because the more you decrease your polarity, the less acidic you are. So in order to determine the effects of polarity, you want to look at the other side. The other side of this negative is hydrogen. The other side for a ketone is going to be this CH3 group. And on the other side for an ester is going to be this methoxy group. You want to ask yourself which one of these is more donating, because the more donating that group is, the less acidic your molecule is going to be, because increasing donation decreases the polarity of the molecule as a whole. And we already talked about the less polarity you have, the less acidic you are. So does hydrogen donate electrons? No. No electron donation. Does CH3 donate electrons? Yes, it does. It donates electrons. And then you want to ask methoxy group. Does a methoxy group donate electrons? Absolutely, it does. Which one donates electrons more? Well, that's something that we're going to learn. CH3 does not donate electrons as much as a methoxy group does. Methoxy groups donate more electrons, more electron donation. Because the methoxy group donates more electrons, it's going to decrease the polarity even more. So if the ester side chain, which is the OR group, is decreasing the polarity even more, it's going to be lowering the acidity even more. So this acidity is going to be the lowest. And then when you compare CH3 and hydrogen, we know CH3 donates electrons more, so it's going to decrease the polarity even further, which makes this a worse acid. And then hydrogen doesn't do anything. It doesn't donate electrons. It doesn't withdraw electrons. So it's going to be able to maintain its polarity, which means it's going to be able to maintain its acidity. So we're going to say that out of these three, this is the most acidic.